Hello, my name is Andrea, and I'm delighted at this opportunity to present my work with Paolo Bozzoni. So thank you very much to the organizers of the Bernoulli IMS One World Symposium 2020, and to you for watching this talk. This work solves the optimal portfolio problem for an investor with reference-dependent preferences in a complete market. What we find is, spoiler alert, that low reference dependence gives rise to a regular regime with a unique optimal payoff, but high reference dependence leads to an anchors regime in which there are multiple optimal payoffs, and what's more, each of which concentrates most of the probability in just one or few levels of wealth. Another interesting implication of our work is that reference dependence helps explain the typical recommendation of financial planners that the proportion of wealth held in equity should decrease as investors age, or, in other words, as the investment horizon shortens. We adopt the framework of Kassegen-Haben, in which preferences depend on a possibly stochastic reference level. Therefore, investors evaluate a payoff Z based not only on its intrinsic utility, but also in comparison with a reference B. And so this leads to an overall utility that combines the classical expected utility component plus a reference-dependent component. Moreover, in the spirit of Kahneman and Tversky's cumulative prospect theory, this function νi that measures precisely the feelings of gain or loss upon deviating from the reference is S-shaped to reflect risk aversion on gains and risk propensity on losses. Finally, the model also incorporates loss aversion, that is, that losses loom larger than gains, by assuming that νi is kinked at the origin and steeper in the loss region. In this work, we focus on the particular case where the gain-loss function is piecewise linear, which in turn reduces reference dependence to these two parameters, eta and lambda. Now, clearly, lambda is the ratio between sensitivity to gains relative to losses, hence, it represents the investor's degree of loss tolerance. On the other hand, eta is the relative weight attached to the reference-dependent component in the overall utility, so it can be regarded as a measure of gain-loss sensitivity. Now, obviously, the choice of the reference plays a crucial role in preferences, so Kassegen-Haben also posit a rule for endogenously specifying references, and these are the only expectations about forthcoming payoffs that are rational, in the sense that they are optimal amongst all alternative payoffs when they're taken as reference. In other words, a personal equilibrium is an actual investment decision that is consistent with prior expectations. Once all personal equilibria have been determined, those with the highest overall utility relative to themselves are the preferred ones. So here we work in a finite horizon and complete market setting with one safe asset with price normalized to 1 and a unique pricing kernel zeta determining all prices. Curly C denotes the set of non-negative payoffs at the horizon that are affordable from initial capital W0. We also impose the following technical assumptions, which imply in particular that the pricing kernel has a continuous and invertible distribution function, and in addition that the classical utility maximization problem admits a unique solution, which we denote here by x tilde. It's now obvious that reference-dependent preferences give rise not to one, but a family of optimization problems, one for each potential reference. A key observation is that each reference dependence maximization problem actually boils down to a classical expected utility problem in which the original utility function u is replaced with this reference adjusted utility. Because these reference-adjusted utilities may be kinked, namely at the atoms of the reference, this means that the corresponding optimizers may have atoms. The main difficulty here then lies in determining the fixed points, that is, the references which are optimal for their own maximization problem. Our first main result identifies the set of personal equilibria, and it relies on the concept of this twist function W, which in turn is motivated by a quantile characterization of the personal equilibria inspired by Jean and Joe. Now, while the monotonicity of the twist entirely determines the number of personal equilibria, their characterization requires the introduction of this family of increasing envelopes of the twist. Although the rigorous definition of this class of envelopes is somewhat complicated at first glance, its visualization is relatively straightforward, as this figure will show. So, given this twist, an increasing envelope of W is any continuous increasing function that lies between the upper increasing envelope and the lower increasing envelope of the twist, and moreover, they increase only when the twist also increases. And so what we observe is that reference dependence gives rise to two regimes. A regular one, where the investor has only one personal equilibrium, and a second regime where there's one personal equilibrium for each increasing envelope. So investors are free to choose amongst infinitely many personal equilibria. Moreover, in the second regime, investors choose levels at which they keep their wealth in intermediate states of the economy and from which they are unwilling to risk deviating. That is, they endogenously create their own anchors. In either regime, the marginal utility of each personal equilibrium is proportional to a twisted pricing kernel. Note in particular that the safe payoff, that is from investing all wealth in the safe asset, is never a personal equilibrium. We also prove some nice properties of personal equilibria, such as regularity, monotonicity, sensitivity to reference dependence parameters, number of atoms, and so on, but unfortunately this video is too short to contain their rigorous statement. Now, in general, the twist can be rather twisted, which makes it difficult to explicitly characterize the endogenous anchors. For this reason, the next result focuses on the more familiar case of a unimodal pricing kernel, such as, for example, in the Black-Scholes model. And so we conclude that one mode leads to two regimes, the regular one, and the anchors regime, where each personal equilibrium has a single atom at these intermediate market states. Moreover, the regular regime emerges when at least one of the elements of reference dependence, whether it's loss aversion or gain-loss sensitivity, are relatively weak. By contrast, the anchors stand out when the combination of the reference dependence parameters is sufficiently strong. Finally, we illustrate our results in the Black-Scholes model for an investor with CRRA preferences. And we see that in the regular regime, which arises when reference dependence is low, the unique personal equilibrium has no atoms and gives up wealth in good states of the world, relative to the classical utility maximizer, to make up for losses in bad states. As for the optimal stock weight, we see that reference dependence depresses demand for stocks, and more significantly so in intermediate states. One of the main novelties of this work is that once gain-loss sensitivity and loss aversion combined become so strong that they override the market, then investors completely abandon diffuse payoffs and instead are better off keeping their wealth constant over a range of intermediate market states which concentrate most of the probability. What's more, Investors can now choose from infinitely many wealth levels between their most pessimistic and their most optimistic rational expectations. In addition, as before, reference dependence entails a lower investment in stocks also for the anchors. In this case, it can even be determined numerically that the preferred personal equilibrium is the most pessimistic anchor, that is the one with the lowest wealth threshold. The last part of this example focuses on how the investment horizon influences investment decisions. And what we find is that there's a critical investment horizon T*, at which individuals switch from one regime to the other. So for an investor with this level of loss tolerance and gain loss sensitivity, the critical horizon is approximately 5 years. So more precisely, when the horizon is long enough that investors can still recover from eventual losses, then investors follow the regular regime. Otherwise, it's just too risky to deviate from the atom, and they remain attached to the anchors. To wrap up, investors with a strong combination of loss aversion and gain loss sensitivity create their own anchors, that is, payoffs that concentrate most of the probability in just one or a few values. Importantly, these anchors are not unique. In addition, in the usual Black-Scholes model, we also see that stock holdings should increase with the investment horizon as recommended by financial planners. If you'd like to find out more, our paper is available at SSRN. Thank you so much for your time. I look forward to any questions that you may have. Bye for now. Take care.